let me continue. So up to last time we recalled the Beilinson's theory. So now the goal is our new goal is to transplant Beilison's work to mix characteristics. But we cannot do it this naively because there are some obstructions. So the first one is that so we don't have cotangent band of the correct rank. So cotangent band is defined by omega 1, but for example, if you take the localization of Z at P as itself, then the omega 1 is just trivial, so we don't get good cotangent band. So this is the first of example. And the second one is that so in the definition of micro support, we have most H and F, and so we consider local acyclicity for the second most F. But here we don't have sufficiently many second most. So in geometric case, if you take any function, then you can get to map to A1. So you have many functions, many morphism F. But for example, if you mix the characteristic case, if you take, for example, A1 over ZP, then and you want to have morphism to one-dimensional object, but it will be just a spec of ZP, and there's only one morphism. So we don't have enough F. So there are such obstacles. So we need to make some variations. So for the first one, so this will be my solution is for this is Frobenius Witt cotangent band. And but I will discuss this later, probably next week. Or at the end of this today. So I start with this one. So the definition of micro support. So we have two morphisms, H and F. And for F, we have C transversality. And also F acyclicity. And F acyclicity. But for H, we have C transversality. But we didn't have a corresponding property. So so this is not symmetric. So I introduce F transversality here first. Okay. So By introducing this property, we can define micro support and consequently singular support. But next task is to prove its existence of the singular support. But to prove the singular support, Beilinson used the Radon transform. That means that we need to use Q and Q check. So we need to have the second map. So first I give definition of micro support using only the first motion, but it will be not enough to prove the existence. So I will need to introduce one more definition. So this will be the goal of this part. So let me start with F transversality. Okay. Okay. So so we studied this motion H, and this for this we are interested in the pullback of our sheaves. So H is motion of schemes. So here I don't need to have. I don't want to have a base field. So this will be general separated motion of finite type of schemes.
So the analog of smooth, is it smooth over the
No. Here I don't need any smoothness.
Okay.
And F is sheaf on X. So here again, I mean this is some object here, and lambda is finite extension of FL and L invertible on X. Okay, so we work with this generality. So we are interested in the pullback of this F by this H. But there are two ways to put it back. So I want to compare these two. So to compare these two, I need to take tensor product. Then there is a conical motion between these two. So this is defined using the adjunction and projection formula. So by adjunction to define this, it's the same thing to define this motion. Then projection formula, I can identify this with F tensor like this. Then we have adjunction from here to lambda. So yeah, by projection formula and adjunction, this motion is defined. So I use this map. Yeah. Okay, now I go back to the the case where we have base field. Assume H is a separated morphism of finite type of smooth schemes over field K. And F is sheaf on X. Then we say this H is F transversal. If this morphism is isomorphism. So this is the definition of transversality. So I can give so in the definition of transversality, assume that H is separated, but we can drop this assumption because so without separated assumption, this morphism is at least locally defined. So we can require that this locally defined morphism is isomorphism. So yeah, this separatedness is such a serious restriction. Okay, so examples. So we have a corresponding property as C transversalities. So if let G be a smooth closed subscheme, smooth over K. Okay, then so if H is transversal to this immersion, then H is I star of lambda transversal. So this is a consequence of the property, purity. And for C transversality, this H is transversal. So we put the conormal boundary here. And in that case, it was equivalent. But here we have only one implication. And the second,
W is smooth.
Yeah. Here W and X are smooth. Yes.
So transversal is in the sense of differential geometry, or in the sense the second line.
Yes. Yeah. This means that the fiber product is smooth and the coordination is right. Yeah. Okay. The second one is that if H is smooth, then H is F transversal. For every F. So in the C transversal case, so she's anything, and if the motion is smooth, then H is C transversal. So this was obvious because in that case the most cotangent boundary is injection, and so the kernel is 0. But so we have this corresponding property, but this is non-trivial. So this is the Poincare duality. Yeah. So Poincare duality says that if you have smooth, and then we have this extraordinary pullback with with shift and twist. Okay. Next one. Sorry?
It's duality. I don't know if you.
Yeah. So I mean that we have a conical here. Okay. The next one is if is locally constant, in H is F transversal. Yeah, if the sheaf is locally constant, such motion is also motion. So, yeah, in the C case, if C is a subset of the dark section, any motion is C transversal. So, yeah, this one is also trivial in that case. Okay, so these are the example.
May I ask a question?
Yes.
So if you have a H and F, for H is F transversal, and then you do a pullback, does the upper shriek commute with the pullback? Like upper shriek, upper star, upper star, upper shriek?
Well, yeah, upper shriek, upper.
Yeah, like if you have a pullback square, you have your H, but then you have a pullback of it, H prime.
H, what is H prime?
I give myself a map from X prime to X.
Yeah.
And then I make the pullback.
Yeah.
It's not necessarily in general not, I think.
Yeah, in general not. Yeah, okay. So the answer is no.
I'm not sure, but
yeah.
It would mean that when you depend on, and so the basic case is the Gizin map, like for hyperplanes.
Yeah.
If the hyperplanes well behave, okay, but then you can cut it down with another one, even another one which is, and then on the intersection of H prime and H, it doesn't need to be.
Yeah.
Maybe in general, I don't think so, but I'm not sure about constructing example.
Right.
It look like.
Thank you.
Okay, so now we have a notion of F transversality and F acyclicity. So let me study the relations. Between transversality and acyclicity. So let me start with some easy case. So suppose we have motion F. So now everything, for the moment everything is over K. Smooth. So everybody here will be smooth over K. And when we take some close point and take fiber like this, and let me call this H. Okay. Okay, and suppose we have called conical subset here. Then yeah. So if so we can consider the condition that f is C acyclic and also H is C transpose. So this is a condition that we consider this map and so the support of this is 0. And this, for this, we consider this map. And sorry. So I assume this F to be smooth, so that this W will be smooth. Okay, then the condition here that the inverse image here is a subset of the zero section. Okay, then what is the relation between these two? So if you restrict this to W, then this is nothing. This is exactly the kernel here. So the condition here means that f is C acyclic on a neighborhood of so we have such equivalence. So let me consider a slightly more general situation. So let be a Cartesian diagram. Smooth schemes over K and assume F is smooth. Okay, then the first claim is that if F is C acyclic, then H is C transversal, and G is H0C acyclic. We have this implication. And correspondingly, if F is universally F acyclic, yeah, so C and X are and F are given. Then similarly, so H is F transversal, and G is H star F acyclic. So we have such properties.
Is it true if instead of assuming F is smooth, you just assume it's a transverse pullback?
Sorry?
Is the lemma still true if instead of assuming F is smooth, you just assume the pullback is transverse?
So if it's by this assumption, so if is smooth on the neighborhood of base of C, so essentially this is not really assumption.
Okay.
Okay. Okay, this claim is rather easy because the combination here means that this pair H and G is C acyclic. So that means the conclusion means that the kernel of T star X times T star V to T star W intersection with H star C cross H star TV is a subset of the section. The conclusion is this condition. And this kernel, because we have this Cartesian diagram, so this is just the image of T star Y. This one. So if the pullback of C is just zero section, then this implies this intersection is subset of zero section. So this is not elementary. Okay. So the second one, the second condition, so G, on G is obvious because we assume universal acyclicity. So the point is that H is F transversal.
Actually, the acyclic and universally acyclic are usually equivalent. Acyclic and universally acyclic, this is usually equivalent.
Yes.
Unitarian conditions.
Right,
But at least in the case you consider.
But
You don't need that for your.
So yes, this universal for acyclicity I need it for G, but for H I just need acyclicity. No, it's not true. Sorry. I also need that. Okay, so because I assume universal acyclicity, so by standard argument, so we may assume I is I. What is I here. I is the immersion. And in fact, I can assume it's closed immersion. Then we can take the complement. So this is the open of the complement and J. Okay, so we take usual triangle. And this one. Like this. And so yeah, so we want to show that the transversality. So we want to show this is isomorphism, but this is isomorphism is equivalent to that this is isomorphism because H is just a closed immersion. So and because this is we can identify this. So it's equivalent to say that this is isomorphism. And this is a consequence of the assumption that F is acyclic. So here I use a proposition. So this is in the appendix of by Illugi in SJ 4.5. So so here is there are more small schemes and F be a sheaf on X. Then the following are equivalent. The first one is this motion is F acyclic. And second one is so for any Cartesian diagram, such that horizontal arrows are immersions. F, H, J. Sorry, maybe to put yeah. So sorry for the notation is different, but to avoid confusion, let me stick to this. For any commutative Cartesian diagram like this, and for any constructible sheaf on V here, so F is here and G is there. Okay, the motion F tensor F star J star G to H star F. So we have a conical motion like this, and this conical motion is isomorphism. So we have criterion for acyclicity like this. And so this is a general thing, and we can apply this to this. So this proposition implies that this is isomorphism by the assumption.
There are two G's here. The morphism, the right morphism is G.
Yeah. So we have sheaf G on B, and the morphism here is G. This is a small G.
Okay. Okay.
Yeah, this is large and this is small. This is small and this is large.
Okay. So this is. Okay. So that's J low star. Where are emergence? Emergence means locally closed emergence.
Yeah, locally closed emergence.
Okay, you reduce open emergence. With some, of course, everything is should be like QC, QS. Otherwise, there are some pathologies. Like for non-quasi-compact open emergence, maybe things. Okay, but maybe you need only minor assumptions.
Yeah. Maybe everything is in Italian, for example. Yeah.
I'm not sure. Yeah, in Illusion maybe it's more general, but I once read it carefully, and you need a little bit more. But it can be complete. I mean, also, anyway, there is a way to justify it. So it's okay. In some cases, one needs to do some induction.
Yeah.
Some which is okay, but it's not.
Okay, so we have this general proportion, and we apply this station to get isomorphisms, and then we get to transversality.
When y is a curve, is it easy to see that this is an isomorphism by using that vanishing cycles vanish?
This isomorphism?
Yes.
I don't know. When the base is the curve and the B is the...
That's a curve. Okay, so the direct image, this is like the R gamma of the inertia on the vanishing side, on psi.
Yeah.
So it's if you know to calculate psi, is if you know that psi is just the restriction to the phi 0.
Yeah.
Then I think you get it very easily, like you said. But it's this is essentially about okay.
Yeah. Probably. Yeah. Okay, so this proves that lemma, and I also give I also state a corollary of this proposition. Okay. So now everything will be smooth over field. Be a Cartesian diagram. Of sorry, I don't need smoothness, sorry. Schemes such that F is smooth and I is inversion. And FB a sheaf X and G sheaf on V. So as in proportion there. And assume this F is sorry. Small f is large f acyclic, and so G is on Y, sorry. This I is G transversal. Then the conclusion is this H up here is F tensor pullback of G transversal. So in particular, so if we take G to be just lambda, then so if we take G to be just lambda, then this transversality is satisfied always, and then just this acyclicity implies H is F transversal. So okay, so this was a statement there, so maybe I don't need to write this. Okay, so using this and the argument like this, I can prove this, but I will omit the proof. So I will just say this. Okay, so this is a preliminary. So now I can define introduce equivalent definitions. Of micro support. So now I go back to this smooth schemes of K. And FB C from X and C closed conical subset as usual. Then the following conditions are equivalent. The first condition is, of course, this F is micro supported on C. So I will give equivalent conditions using transversalities. The second one is, so let HF be a pair of morphisms. Over smooth schemes. Okay. Such that so usual condition, the same condition as here. So H is C transversal and F is H not C acyclic. Then so the corresponding property, morphism has the corresponding properties. The first morphism H is F transversal and the second morphism is acyclic. So this is new. So in the definition here, so it's the same, except that we don't have this condition. So we can impose this condition here to get the equivalent condition, equivalent statement. Yes.
Okay. So you add the H is F transversal and it is equivalent to the one without adding it?
Yeah. So the first condition is defined without this condition, but the first condition implies this condition, actually implies this condition. And I have one more equivalent condition. So we consider H and F as before, and such that this pair. So we regard this as a morphism from W to X cross Y. And so last time we said that I said that this condition there is the same as that this is C cross T star Y transversal. So up to here, it's written differently, but it means exactly the same thing. Then the conclusion is for any sheaf.
This is the same assumption as before or not?
Sorry?
This is the same?
Yeah, this is exactly the same.
Okay.
Yeah. Then for any G on Y, this morphism is this external product transversal. So this is the usual notation. This is just to put one star F tensor put star G. So this is living on X cross Y. So the condition on this H and F can be stated like this using transversality. Then we can naturally expect that this is related to the transversality of sheaves. But here, so this C is related to F, but we get a new second factor T star Y. And so we have seen that any sheaf on Y is micro-supported on T star of Y. So we can put anything on the second factor. So this is the condition. And we claim that this we can formulate equivalent condition like this. Okay, so let me prove. So this implication is clear. So we start with this. So to prove this, the only difference is this F transversality here. So we need to show that so the C transversality of H implies C transversality of F transversality of H. Of course, here we use the assumption that F is micro-supported on C. Okay, so again, by standard method using this decomposition, so we may assume H is immersion. So here we also need to know the transitivity of F transversality, but I will skip this kind of routine. So by some standard argument, we may assume that H is immersion. And this transversality is a local condition, so we can we can find this Cartesian diagram, and this F is smooth. So we may assume to have so locally, we can take equations defining W, and we define map to affine space using these equations. Okay, now, so by this assumption, so this H is C transversal. So this means that this our F map here is C acyclic on the neighborhood of W. But of course the question is local, so we can forget this. Then since we assume that our sheaf F is micro-supported on C, so this implies F is F acyclic, because F is micro-supported on C. And then by that lemma, this H is F transversal. Okay, so we can have this extra condition. Okay, now okay, we show the equivalence of this and 3 over there. So this 3 is moves from W to X cross Y, but as usual, I decompose is like this. So we want to, so the condition 3 is transversality for this pair of motion, and the first one is of course identity equals F, and the second one is H cross identity of like this. Okay. Okay. Then we consider we compare F transversality of H, and so here we get this motion for energy. So this is on this, and we also need to compare. Yeah, this is there, and now H star F acyclicity of F, which is there, and here 1 F H star F transversality of it. So this is also for every G of Y. So we compare this property and that properties. Okay, so we start to from here. Okay, so we start from this. Now, so this P is not the characteristic, but I'm sorry that I don't have enough alphabet. Let these PBs are conical motion. Then the C transversal, H is C transversal, means that HP is C cross T star P transversal. So this is obvious. So yeah. Now, so we want to we are proving the equivalence like this, and P is just 1 point. So the second property implies that this means this implies F transversality, and the third one implies this HP is transversality. But here this P is just a point, so in fact this also implies this. So in any case, if the condition 2 implies condition 2 and condition 3, either of them implies the F transversality of H. And we have this implication. So that is the following lemma. Yes. Sorry, lemma 3.7 is missing. So let H be a more smooth. And assume that this is F transversal. Then for any Y, so for any Y and for any G on Y, this product motion is G transversal. Sorry, F. Transversal. So this is a consequence of corollary 3.5, I think. Yeah. So we consider yeah. So yes. So we have sheaf G here and F here. And this H is F transversal. And sheaf G is, so this is universally G acyclic by the genic local acyclicity. So, so the projection here is the first projection is locally acyclic with respect to this pullback. So this is acyclic. So why must be smooth over here?
You are now proving lemma 3.8.
Sorry?
You are proving now.
I'm proving that this map here is this transversal.
Okay.
Yeah.
Using corollary 3.5. Okay.
Yeah. So we have transversality here and acyclicity there. Then the lemma corollary 3.5 is that the motion here is transversal with respect to the tensor product of this guy and pullback of that guy. So corollary 3.5 says that let me call this says this H cross 1 is F star F tensor this transversal, but this is exactly this tensor product. So so either 2 or 3 implies this condition, and this condition always implies this condition. So this part is somehow automatically satisfied in both cases. So sorry, this part. So this part is essential. But maybe I take a break here for 5 minutes and I will continue with this part. Okay, so this part is somehow done. And I have, so the problem is divided into these two parts, but to justify this division, I need to use some transitivity, but I will skip this part, this argument. So now this number 2 implies this acyclicity, and the number 3 implies this transversality. So this transversality. So we need to have this equivalence. Now, so this equivalence is a consequence of this proportion. So this is Braverman, Gaitsgory. So slightly modified. So let F be motion of schemes over excellent regular Neutralian schema S. And F be a sheaf on X. And I assume that this motion is universally F acyclic. So this condition is satisfied if S is just a spec of K. And where was, yeah. then the following are equivalent. The first one is this F is F acyclic. The second condition is that for any constructible G on Y, the motion is this transversal. So they proved the case where S is spec K and they work with QL sheaf. But I can't follow the proof in the QL sheaf case, but in my case, our sheaf is a sheaf of lambda modules, and I checked the proof in that case. So today I will not give the proof of this, but next week I think I will have time to talk about the proof. And if we admit this proportion, then we get this equivalence, and that that proves the equivalence of 2 and 3. Okay.
The regularity of S is important here?
Sorry?
Is it important that S is regular?
That I'm not so sure.
Okay.
Maybe not.
So when you define transversality,
Yes.
it was the general notion, but you need some assumption on the with the upper Schreck factor, yes?
Yeah, yes.
Okay, I mean you can do it, but you don't define this assumption on X and Y, or so X and Y are not necessarily our finite type over S, or
sorry. Yeah, I said that X is. I'm sorry. I forgot to write that. Y must be smooth. Yeah, and probably of schemes of finite.
okay, maybe this is not essential, but
Yeah, but yeah, this is necessary. Yeah. Yeah. Okay, so now we have this equivalence, but this equivalence is not enough for us. So here K is any field, and if we assume that K is perfect, then we can actually omit this second most F. That is the next proposition. So X smooth over K. So it's like this. So the assumption is the same. F is on X and C is closed conical subset. Then the following are equivalent. Then the first condition is the same. F is microsupported on C. Sorry. So we consider these conditions. So the first one is one is the same, and the second one, the support of F is a subset of the base of C, and let H be most of smooth schemes. Over K such that H is C transversal. Then so we have only this condition, H is F transversal. So we consider this condition. So in this second one, we omit F and we just consider the first most H. Then we always have 1 implied 2, so that is part of this. So this is we have already seen. But if we have the inverse, so if K is perfect, then we also have the converse. Okay. So let's prove this. So as I said, why is 1 plus 2 already done? For okay, perfect. Okay, so we want to show that yeah, so this transversality part is okay. So transversality part was not included in the definition of microsupport. So we need to show this. So assume HF is C acyclic. So assuming acyclic, and then want to prove if the second motion is H star acyclic. Okay, so again by using transversality, we may assume. So we reduce the case where H is just the identity. Okay. Then and after shrinking, so because we assume that the support is a subset of base of C, and then C acyclicity means the smoothness on the neighborhood of the base. So we may assume, we may also F is smooth. Then so in the first section, we studied the relation between transversality and acyclicity, and we just see. So there, I just stated the implication from acyclicity to transversality, but so here we want to go the other way. So the second so from here we have only transversality, and now we want to show the acyclicity. So we have to go the other way. So it's given by the following lemma. So F is more smooth. Of schemes of finite type over field K, and F be a C from X. Now assume for every Cartesian diagram, so we have a map from X to Y. And P prime, F prime, G, H, I. Such that so I is immersion, and H is, so our sheaf is here, and assume that this H is transversal, this is to the pullback of F. And the schemes here, so Y prime and Z, so they are smooth over some finite extension of K. And map, so we are considering basically alteration. So P is proper. And generically finite. And the I is closed imagine. So we consider any such Cartesian diagram satisfying this condition. So so this is proper and geometrically finite, and I was repeating this. Proper plus geometrically finite, and I is immersion, and yeah, and this is condition. And so we assume this transversality for such every such Cartesian diagram. Then the conclusion is that F is F prime acyclic. F is F acyclic. So the assumption is rather complicated, but basically this means that we work over some alteration and assume transversality for the pullback on the alteration. And this image.
Finite is generically on the base or on the source? Because a generically finite means on an open dense of Y it is finite.
Yeah.
But it could be, let us say, empty on an open dense of Y and you just have a sum.
A generically finitely on Y, on the base. Okay. Yeah. Yeah, this means that transversality implies acyclicity. So we can prove this by using alteration, but I omit to prove.
Sorry, so the statement is assumption is for any Cartesian diagram with YZ smooth finite type, P proper geometrically finite, I close the margin.
Something wrong. Yeah. Thank you. So we consider any such diagram, then we have for any such diagram we have this H is P prime star F acyclic, transversal. Then this implies F is F acyclic. Yeah, thank you.
I think it should be even true with curves. That's testing on curves. Assuming constructibility and so on, so it's probably it's enough to test with smooth curves over finite extensions of K mapping to the base. Smooth curves. Just with curves, so, and then of course you can make it proper by, this is not by compactifying, but I think that because anyway, we can make some alteration or modifications, but you have a good theory of vanishing cycles, and then you can make some test on. But I don't know what is your argument.
yeah. I don't want to go into the proof of this. So let me just admit this. Okay, so yeah. So we consider such. So we want to apply this to this situation. So so we have C here, and we have map here, F here, and F is smooth, and F is C acyclic. So yeah, and now. So here, K is just a finite extension. So in general, this can be inseparable extension. But our assumption that so K is perfect, so this is a finite separable extension. So it means that this must be smooth over K. So we can use so now everything is smooth over K. So this implies that the C acyclicity of F implies that P prime and also H prime, so they are C transversal. So as we have seen before, so it was 3.3. Yeah, 3.3. So this implies, so we are assuming that C transversality implies F transversality. So they are F transversal by condition 2. And by transitivity of transversality, this implies that H is F P prime star transversal. So by this 3.11, F is F acyclic. Okay, so using the other implication of the other direction, we can check that this first condition is enough to prove enough to formulate micro support under this assumption.
This lemma, where is it written? This lemma, where is it written?
This lemma?
Yes.
Yeah, this lemma is written in this inventionist paper.
Okay.
Okay, now, okay. So we have seen equivalent formulations. Now we can go to mixed characteristic. Okay, so at the beginning today, I said that there are two obstructions. So the first one is that we don't have a good cotangent bundle. So so we discussed this problem. So for simplicity, let me now fix S is spec of OK. So OK is DVR mixed characteristic. and and residue field little k is perfect. And X will be a regular scheme of finite type over yes. So I can weaken the assumption a little bit, but for simplicity, let me stick to this simplifying assumption. Okay, so so we want to have a cotangent bundle such that at a closed point the fiber is the cotangent space. So the rank should be the dimension of X. So I don't know how to define such a vector bundle, but instead, so we will define a locally free OX FP module F omega X of rank equal dimension X. So sorry, X is
Of course, you assume that the dimension is, let us say, it's equidimensional.
Yes, yeah.
Okay.
Yeah. So we will define local free, rank is dimension, and at every at any point on the closed fiber, we have exact sequence. So not only at the closed point, in general, the fiber, so here we have absolute differential, so over Fp. And here, this F upper star means the base change by the absolute Frobenius. So at every point on the closed fiber, we have such exact sequence.
Sorry, maybe I misunderstood something related to Ofer's question, but so like, what if X is like A1 over the generic point?
If you have only generic fiber, then it's just 0.
So, but when you say the rank is equal to the dimension of X.
Yeah.
So that's okay. So 0 is a vector bundle of rank 1. Okay. Okay. 0 is a vector bundle
of rank 0.
Okay, but then
No, okay, but it's
just
like
a
one
special
of the
file.
empty set. Over the empty set,
it's also rank 1. Yes. Yeah.
On empty set, rank can be anything.
Yes. Okay.
No, but let us assume that that X is irreducible and meets the special fiber.
Yeah.
And then it would be okay. And otherwise, you can have different components.
Right.
So you don't want.
Okay, thank you. Yeah, it all makes sense.
Okay, so we want to define such object. So how we do that? Frobenius Witt cotangent bundle. Okay, let me begin with the definition. So P will be prime number. So first I define polynomial. So P is sum. So this is capital P. I equal 1 to little p minus 1. So this is a binomial coefficient divided by P. So this is integer and x I to p minus I. So this is x plus y to p, xp, yp divided by p. Okay, so we have this polynomial. So A be a ring and M module. Then we say a mapping W into A. Sorry, the other way. A to M is Frobenius with derivation if or so this is long, so I will just write Frobenius with if for any element we have, so for the addition, so we don't have exact activity, but we have this polynomial times WP. So we modify this addition and for the multiplication, so we modify the Frobenius Leibniz rule by this piece power. Okay. Yeah, so this is the definition. So the name comes from, so here we have piece power, so it's Frobenius, and this polynomial, So this polynomial appears in the addition of Witt vectors of length 2, so it's called Witt. Now, F omega A. So this is the module of Frobenius Witt differentials. So this is A module representing the functor. Sending A module M. A module M to this Frobenius Witt differentials, derivations. Eta. So this is the definition. So let me give you some formula. So if the W is a Frobenius Witt derivation, then for integer, we have such equality by induction. And similarly, for A, we can compute WNA like similarly. By induction. And if you compare this equality and that equality, then we get n to p minus n q's WA for any A and n. So if this implies so if A is the algebra over this localization, then p times this module is 0. So we get something supported on only on characteristic P fiber. But if A is so yeah. So in the following, we always assume this. So F omega A is A divided by PA module. And if A is regular of finite type over okay, like there, then this is locally free of finite rank. and the rank is.
You mean F omega A is locally free of finite rank?
Ah, yes. Thank you. Yeah.
Over A and PA. Over.
Ah, yeah. Over finite rank over. Yeah. Locally free. Yeah. So this gives, so if x like that, then f omega x, so this is locally free. OX FP 文字よ。So this defines vector bundle. Yeah, ft star x. So this is vector bundle associated vector bundle on XSP like this.
So this claim that the F omega is supported on the closed fiber. What was the logic? Could you explain that logic again? Why it's supported on? Why is it supported on?
This is just for.
And it's Q by P.
Yeah, I couldn't follow the calculation.
Because you take n equal p, for example, and then you get that this is divisible by p once.
If you just take n to be p, then the valuation of this is 1.
Sure.
Yeah. So it's killed by p. If you assume
and that being 0, what was the?
Equals 0. Yeah.
How do you do it? How did you get it?
This 0?
Yeah. So.
Yeah, you just compare this and you can put b to n.
Okay.
Yeah, then this part is the same, but this you compare this and that. So b is n.
Sure.
Yeah, then you get this.
And if X happens to live over the special fiber,
Yeah.
is then just the Frobenius pullback of the usual cotangent?
Exactly.
And is that easy to see from the algebra?
It's
WP
It is easy to get the W0 and W1.
Yeah, WP is 0, so you just Kähler differential twisted by Frobenius. Okay. So we get this. So this is Frobenius bit cotangent bundle. So the problem is that this is only defined on the character P fiber, but the good point is that this has a correct rank.
So it looks like that you get, in general, if you work over non-ZP algebras, if A is not over Z localized with P, then it could be in some cases that some other primes, you will have some junk.
Maybe, but I never studied seriously, so yeah.
just for Z itself, you could probably, because you get things like for Z, okay, it's not, but of course, a basic property of differential is like compatibility with a tull morphism and smooth morphism and so on. So this should also work for your definition.
Yes.
But probably you have to work over ZP algebras because this thing with n to the p minus n, this argument doesn't quite work because of you work very small residue field. But if you can enlarge it, you can. But I don't know. Maybe you need. But you always need this condition.
Yeah, I always assume this condition, so I don't know what's happening outside. Okay, so if x is smooth over this is, or more generally, maybe and xy like this, then we have ft star y, yx, ft star x. So they are vector bounded on the.
Is that regular?
Yeah. This is regular finite type. Then we have relative. So this is associated to omega 1. So this is smooth. So this is locally free, and restricted to character P fiber. Then we can take Frobenius pullback, and so we have such exact sequence of vector bands.
So for any like if A to B is smooth, then the Frobenius with differential of B should fit in a short exact sequence. Like the usual one is the Frobenius twist of This is this is what you
Okay. Now using this, I can define singular support or first micro support. So x x regular scheme of finite type over S like there, and F be a sheaf on X, and C be a closed conical subset of Frobenius Witt cotangent boundary we just defined. Then we say F is micro supported on C if the following condition is satisfied. So first, so it's just erased, but I need to impose the condition on the support. And so Frobenius Witt cotangent boundary is defined only on the closed fiber, a character P fiber. So I have to take the restriction, and this must be a subset of the base of C. So this is the first condition, and then so let H be a so most of regular schemes of finite type over S, and if H is C transversal, then C transversality should imply H is F transversal. But again, we work only on the, so this is defined only on the closed fiber. So we can impose this condition on some neighborhood of characterized P fiber here. So the C transversality again, this is defined as before. So we have in the same way. So this intersection is a subset of the zero section. Okay, so this is the definition. So I will discuss this more on Thursday.
Thursday or Monday?
Yes.
On Monday. On Monday.
Oh, no, sorry. Yeah, next Monday, yeah.
Okay, so.
Okay.
Any questions, comments?
Do you use, so for this thing with alteration, this 3.11?
Yeah.
Okay, so so which what do you use there? Like, do you use like Orgogos's paper on nearby cycles? So what kind of thing you use?
Yeah. You're asking the proof.
Yeah.
Yeah. Yes. Yeah, if I took alteration, but if I don't take alteration, and if this is just y, then the acyclicity relation between acyclicity and transversality, we can yeah, we can use another proposition to relate to them. Yeah, we can use proportion 3.4, which characterize acyclicity, and so so there I used yeah. So the transversality was formulated for H, but we can take the complement open immersion and we can apply that proportion.
Yeah, of Gaitsgory, okay.
But but to get regularity, I need to use take alteration. That was the basic idea, but I cannot recall the detail.
The 3 point, was it the one proposition?
Yeah, proposition is 3.4, and before that, so I explained the proof of lemma 3.3. So lemma 3.3 is that proportion, transversality for the closed image, to study the transversality for the closed immersion, I work on the complement of immersion.
Okay, okay.
Yeah.
Yeah, okay, so there was no, what do you say? I have, okay.
Yeah, basically I use this kind of argument, but I have to work with alteration and sorry, I can.
Yeah, 3.4. No. Okay, you have this with coefficients, and then you make an alteration to make it not okay.
Yeah.
Okay. Okay, that's another way. Okay.
Okay, so let's thank Takeshi again.